Patty Simpson with Simpson Math. Let's look at the central limit theorem and how we use it. So the central limit theorem tells us that for all populations with a mean, remember we represent the mean with that Greek letter mu, and a standard deviation where we represent the standard deviation with the Greek letter sigma, a sampling distribution of sample means will have three characteristics. If the sample size, where we represent the sample size with the letter n, is at least 30, or the population is normally distributed. So in other words, for whatever shape my population is, that distribution of my population data is, let's say the population data is skewed to the right, or my population data is skewed to the left, or maybe my population data has a nice normal distribution. No matter the shape, when I go into that population and I pull a sample and I find the mean of that sample, and then I pull another sample of the same size and I find a mean of that sample, and then I do that over and over again, and I create a whole new distribution of those sample means. Each one of those means I create a whole new distribution of. That new distribution will have these three characteristics. The first characteristic is the mean of that new distribution, that sampling distribution of sample means, the mean of that distribution will be about the same as the mean of my population. Then the standard deviation of that new distribution I've created, that sampling distribution, will be equal to the standard deviation of my population distribution divided by the square root of my sample size. And then the third characteristic is the shape of that new distribution, that sampling distribution of sample means, will approach normal. No matter the shape of that original distribution, it will approach normal. As long as my sample size is at least 30, or if my population is normally distributed to begin with. And then the larger the sample size, the closer to normal that sampling distribution is. So with that knowledge that this new sampling distribution of sample means has those three characteristics, we can begin to answer some questions about the sampling distribution after collecting a few samples. So here's an example. Some health reports claim that the mean duration of a cold is 7 days, with a standard deviation of 2 days. If samples of 100 people with colds are taken and the length of the cold is recorded, what would you expect the mean of the sampling distribution of sample means to be? Well, think about that for a second. In my population, people get colds, and the average cold is 7 days. Maybe some of them have less than that, they have more than that. Maybe that distribution is skewed to the right. And I go out into the population and I collect 100 people and I ask them to record how long their cold is. And then I do that all across the United States. I pull a sample of 100 people and I create a whole new distribution of sample means. I want to know what would I expect that mean of that distribution of sample means to be. And I know from the central limit theorem that the mean of my sampling distribution, so this is the symbol for the mean, and then this little X bar is because it's a distribution of sample means, should be equal to the population mean. Well, we know that our population mean was 7. So the mean of our new distribution will also be 7. What would you expect the standard deviation of sampling distribution of sample means? So what would I expect the standard deviation to be of this new distribution that we've created of sample means? Well, I know from the central limit theorem, again, sigma tells me I'm talking about standard deviation. This little X bar means that it's the standard deviation of the sampling mean of the sampling distribution of sample means. That should be equal to the standard deviation of my population distribution divided by the square root of my sample size. So here, my population standard deviation was 2 days. I'm going to divide that by the square root of my sample size, which is 100. So 2 divided by 100, the square root of 100, which is 10, is just equal to 2/10. I know that the standard deviation of this new sampling distribution is 2/10. So I know a little bit about my sampling distribution of sample means. I know that the mean should be about 7, and my standard deviation should be 2/10. And then I'll also know that it'll have that nice bell-shaped curve, that normal distribution. And I can use some of my normal distribution rules, like the empirical rule, to help me to find probabilities within that. So let's use the fact that we know that this sampling distribution of sample means is approximately normal to find a probability. So here's an example of that. The same problem, some health reports claim that the mean duration of the cold is 7 days with a standard deviation of 2 days. If the sample of 100 people with cold is taken and the length of the cold is recorded, so we've got the same setup, but here at the end our question has changed. What's the probability the mean duration of that sample of 100 people, that mean, is between 6 6/10 and 7 4/10 days? So in other words, we've gone out and we've collected the duration of a cold from 100 different people. And we find a mean from that. And we want to know what is the probability that that mean is between 6 6/10 and 7 4/10 days. Well, we know that that mean belongs to this distribution of sample means. And we know that this distribution of sample means is approximately normal. So now we can use our normal information about the normal distribution to help us find that probability. So first thing I'm going to do is draw this distribution that sample mean belongs to. And that sample mean belongs to a distribution where, remember, right in the middle, I'm going to put this mean of 7. We expect the mean to be 7 because our population mean was 7. Then our standard deviation of that sampling distribution is 2/10. So I'm going to count up 2/10. So to 7 and 2/10, count up another 2/10. 7 4/10. I'm 2 standard deviations up one more standard deviation, and I'm up to 7 6/10. That's 3 standard deviations above the mean. If I count backwards, I'm at 6 8/10. That's 1 standard deviation below the mean. Count back 2 standard deviations below the mean, and we're at 6 6/10. And back 1 last deviation, and we're at 6 4/10. So this distribution of sample means we know is approximately normal. So we know its peak will be here at the mean, median, and mode will be about the same. And we know at each one of those standard deviations we have an inflection point, and it's symmetric. So both sides of our distribution should be approximately the same. We should be able to fold it. So I'm going to draw my bell-shaped curve here to show that normal distribution. And this sample mean that we've collected from this sample of 100 people falls somewhere in this distribution of sample means. And we want to know what's the probability that it is between 6.6 and 7.4. What's the probability that that mean falls somewhere in here in our distribution? Well, we know from the normal distribution and our empirical rule that 95% of our data falls within 2 standard deviations from the mean. And in this case, our 6.6 is 2 standard deviations below the mean, and our 7.4 is 2 standard deviations above the mean. So we've gone out 2 standard deviations, and we know from the empirical rule that 95% of the time, or 95% of my means will fall with that in that range, or 95% of the area underneath this curve is between 6.6 and 7.4. So we expect, or the probability that we get a mean from those 100 people that is somewhere in between there is 95%. This is what makes the central limit theorem so very powerful. The fact that we know that this distribution of sample means is approximately normal lets us know that the probability that the mean of this sample is between those two values is 95%. And because we know no matter what the distribution started with from our population, that new distribution of sample means will be approximately normal, we can use all of our information about normal curves to help us to find out about means of samples. So the central limit theorem is an extremely powerful theorem that we use in statistics. Math Made Simple is Simpson Math. Thanks for watching.